All right. It's very important to realize, and I hope you do, that the Starshot system is a system. It's not a bunch of components. And technologists tend to look at this shiny object technology and that shiny object, but it's a system. It has to work together. You didn't get here on an airplane that was just made up of parts. It was a system, a totally integrated mechanical, chemical, and electrical system. Therefore, we're going to start looking at Starshot in detail with the next speaker, who is going to talk about it as a system. Now, Dr. Kevin Parkin, a good friend of mine, is the systems director of the Breakthrough Starshot project and the founder of Parkin Research LLC and the inventor of the microwave thermal rocket. In 2005, he was awarded the Korolev Medal by the Russian Federation of Astronautics and Cosmonautics for his groundbreaking work on microwave thermal propulsion. And in 2007, Kevin founded the Mission Design Center at NASA Ames. And since then, he's been principal investigator and chief engineer of a $3 million DARPA-instigated project to build a small millimeter wave thermal rocket and launch it. And in fact, they did. This resulted in the first millimeter wave absorbent refractory heat exchanger, the first millimeter wave thermal rocket, and the first high-power cooperative target millimeter wave beam director. That is the thing that points at and keeps the beam on the rocket. He has a PhD from Caltech, a little-known place in Southern California. And so please join me in welcoming Dr. Kevin Parkin.
Thank you very much, Jim, for that kind introduction. So good morning. So I'm Kevin Parkin. I'm the system director for Breakthrough Starshot. If we could bring up the slides. So one of the responsibilities of the system director is to oversee the system model that models all aspects of the Breakthrough Starshot idea. And so what I'm going to present this morning is the system model for Breakthrough Starshot. It's both the formulation of the model and the results that we got for the mission that is the 20% the speed of light. I'm also going to present a point design for a solution at 1% the speed of light and a point design for a ground-based facility that tries to achieve a velocity of 70 kilometers a second. So to begin with, let me define Breakthrough Starshot. The objective is to send 1 gram of scientific payload to the Centauri system to image any planets that we may find there, and to do this by carrying that instrumentation with a sail that's accelerated by a beam that is sent from the ground. And the capital cost of this system should be less than $10 billion. So that's the definition of Starshot. The sequence that this implies is step one, you launch a carrier vessel, and actually Pete Klupar went through this just a minute ago, so I'll do it again. But you launch a carrier spacecraft which contains a number of sails, and you deploy one of them, and you acquire it with the beam director. And once you've acquired the sail and entrained it, then you turn up the power on the beam and you accelerate it to your desired cruise velocity, which in this case is 20% the speed of light. Step 4, after you've finished accelerating, is that you're in a cruise phase, and to Alpha Centauri it would be 20 years. As Pete Klupar already mentioned, there is a dust environment, and you might want to turn sideways so that you don't get so much damage due to the dust. On the other hand, you might want to face Earth for periodic communication. Step 5 is that you enter the Centauri system, you perhaps discover new planets, and you collect photons, and you analyze data, and you're going to have to do that autonomously because you've got 4 light years, so you're not going to be deciding from Earth. You're going to have an AI system on there that is deciding what's important and what to do in step 6, or which things get relayed back in step 6. So step 6 is to relay the data that you find back to Earth, and do it before your sail is shredded by dust. So one of the things you'll notice as you talk to us is that breakthrough Starshot is not a single concept. Pete Klupar talked about breakthrough Starshot. Phil Lubin talks about breakthrough Starshot. I'm going to talk about breakthrough Starshot, and they're not mutually consistent. Each person has a different idea in mind exactly of what the solution is. So rather than suppress any particular point of view, the approach at this very early stage is to label each school of thought and track it. So I want to just outline the three main concepts. Pete Klupar talked about this one on the right, where you have electronic functionality that is lumped on a traditional style chip. This chip is actually very heavy relative to the sail, and so you need to transmit forces around the sail to deal with the stress concentration that causes. That's one school of thought. On the left, you have an alternate school of thought where you integrate the sail functionality into the sail and you spread the mass out. And then more recently, the middle concept here is that rather than a flat membrane, you can have just a bubble, which is stabilized by gas inside. That's something that Harvard's been looking at. So our approach is to collect information on these concepts, to collect technology alternatives, label everything and track it so that we don't sub-optimize by kind of pre-guessing which technology emerges victorious. And I should say, though, for the analysis I present in the remainder of this talk, I analyze just the dielectric circle. So I'll talk about that in a minute. So the context of this work, it doesn't exist in a vacuum. It's built on work that was done by many others, very notably Robert Forward in 1984. There was a lot of conceptual progress and sort of analyses that have started to pin down what a beam-driven sail should be. Most recently, Phil Lubin generated the initial point designs for Starshot, as did a team at Harvard led by Avi Loeb. These initial models were spreadsheet models. They didn't integrate trajectory so much. They were hand optimized. So the version of the system model that I'm going to present to you now is a later version where you integrate trajectories and there's automatic optimization so that you meet the exact cutoff velocity and you minimize the overall cost of the beam director and things like that. So first of all, the system engineering process is an iterative process. You don't just start with requirements, then solve everything, and then out pops a sail. You take a few turns at producing, refining the idea. So we start with the initial goals and recognizing the opportunity that now is a time when we can actually build one of these sails, that it doesn't violate physics and that we have a basic grasp of the engineering involved. The initial goals were to go to Alpha Centauri, to reach 20% the speed of light. These were articulated in April 2016, basically. Then we created the initial concepts. These are two of them that I've already shown. There was an initial trade study that was a year ago, and some requirements that were generated from that. And now we have the discovery of Proxima b, so that's another target to go to. And we have the addition of this gas-filled sail concept. And we are here, we're probably on the second or third iteration around this spiral. So we're refining the system design, and I'll talk about this next. So the system model. The system model begins with the beam director, which we've shortened to beamer. It's just an aperture. It has a diameter, it has a certain intensity that it transmits at, and it has a certain aerial cost, so dollars per square meter, dollars per watt, and storage cost, dollars per kilowatt hour. There is a second aperture, which is the sail itself, and it's at a distance z, and it also has a diameter. And the problem is to transmit energy from the beamer to the sailcraft. And when you do that, the sailcraft accelerates, and it accelerates to some distance. And that is the top level system model. It is just a trajectory integration. The trajectory integration itself is just in one dimension at the moment. There's no need to make it harder than that just yet. It just does a runge cutter integration, and it uses a relativistic equation of motion. The intensity, so the way the intensity goes down as you get farther away from the beam director is modeled as an idealized Gabao beam. So it's not a Gaussian to Gaussian transfer. There is a model that does that, and I'll explain that in further detail. Also, your sail has a reflectance, a transmittance, and absorptance, and there is an optical model that recalculates that at every step of the trajectory integration. So that's also rolled into the system model. So I'm going to start with the Gabao beam. These are used in wireless power transmission. So they were used a lot when they were looking at space solar power, for example. And the reason they're used is because they describe near optimal transfer of energy between two finite apertures. Gaussian beams are infinite in extent. And when you're doing wireless power transfer, the area of your apertures is something that you want to minimize. And it costs a lot of money to make those apertures. And so Gabao beams tend to be used for that purpose. They're similar to truncated Gaussians. So on the bottom right-hand side is, if this is the axis of the beam, this is the way the intensity drops off as you go away from the axis of the beam. So a very high efficiency Gabao beam looks like a Gaussian, and then as you truncate it because you can't afford the aperture, you get something that is closer to a truncated Gaussian. So it's that sort of a solution. Top hat beams, so that is where you have just a step function which then transforms to a sinc function in the far field. They're less economical. So they spill more of the beam for the area that you use to transmit. So the efficiency of beam transfer, so if you've got an area here and you're transferring to an area here, the efficiency is described by this universal parameter tau, which relates the area of the apertures and the distance between them and the wavelength that you're using. It turns out that it's just that parameter that defines the efficiency. This is a plot of the efficiency, and I'll show you how it relates. Eta is the efficiency. It is a function of A. A is related to tau. As tau increases, the efficiency of transfer goes down. This curve is used a lot in wireless power transfer. People who have read the literature on this will probably recognize this figure because everyone uses it, because until now there wasn't a closed form expression that reproduces this diagram. So I derived one and published it. So there is now, and that's really useful when you're doing numerical optimization. The equation of motion just begins with Newton's second law, so force is mass times acceleration, which is equal to the power divided by the speed of light. This is the absorptance, this is the reflectance of the sail. And this pertains just to a circular sail that's dielectric. That's just the one case. Once you move to higher speed, there's this extra factor that comes in of 1 minus beta, where beta is your speed divided by the speed of light. And so if you have an area that's moving away from you, then photons don't hit it as fast because it's moving away really fast. If you then take into account special relativity, you also have redshift of the reflected photons, which gives you this extra factor here. And then if you want to include sail recoil, it gets even worse, and you have these factors here. But these two factors here are of the order 10 to the minus 30. And so essentially it just reduces back to this case. So this is the equation that the system model is integrating. So this is the acceleration here, this is the mass of the sail, and it is integrating that equation in one dimension. So space-time diagram. So you have an observer, the beamer here, you have time on this axis, and you have space on this axis. And your beamer turns on, if I press the right button. All right, your beamer turns on, and your first photon goes at the speed of light this way. So you've got a straight line this way, and then it stays on for an amount of time, TP, until you've got the last photon when it turns off again. Then you have your sailcraft. Your sailcraft starts out stationary, so it's just a straight line going upwards because it's not moving along the x-axis to start with until it encounters the beam. The beam accelerates it, and then you go off at a constant velocity thereafter. So that's what that looks like on the space diagram. But the reason I'm showing you this diagram is because there's an extra thing that you don't think about, which is that the sailcraft is accelerating for longer than this time TP. It's actually got this extra time here. So the time that you're accelerating for, because we're going to 20% the speed of light, is about 20% longer than the beam is actually on for. And that makes a difference to the calculations. From the point of view of the sail, because you're moving away from your photon source, you're receiving less energy by this factor of 1 minus beta. And that's actually classical. It doesn't matter if it's photons or raindrops or anything. That happens right from the start. And then, if you take into account special relativity, you get this extra factor of gamma that you also divide by. So there's a few details in that. Moving on to the optical model. So when you look at the window, the amount of light that the window reflects is a function of the angle that you're at relative to the window. And it's also a function of usually what color you're looking at as well. And so there is a stratified layer model in the system model that describes how the reflectance changes, the reflectance of a sail, which is a very thin film, changes with the thickness of the sail, changes with the angle that the beam hits the sail. And that is part of the system model as well. So I have a little quiz. Which is better? A 1,000 nanometer thick sail with 99.99% reflectance, or a 100 nanometer sail with 25% reflectance? And this is a very important question because it goes back to what the real figure of merit is here and what you're driving towards. Now, when I presented the equations of motion, this was one of the equations of motion, and I claim that what we care about is the amount of acceleration that your sail gets per watt of energy that you've spent accelerating it. If you rearrange this equation, you get that the acceleration divided by the power is proportional to the reflectance of the sail divided by the thickness of the sail. So people, when they talk about this, have gotten kind of fixated on a high reflectance. It's not, that's not the figure of merit. Really, the figure of merit is the reflectance divided by the thickness. And actually, this second case here accelerates 2.5 times faster than the first case. So there's no point in going for higher reflectance if you can get it thinner, usually. And you can use the stratified layer model to show that. So you get this first peak in reflectance at a quarter wavelength. And because it's reflectance, every quarter wavelength as you go thicker. But if your figure of merit is reflectance divided by thickness, then the first peak is really high, and now it goes down to a seventh of a wavelength. And thereafter, it's much lower, so you get lower performance. So this result was first obtained by Jeff Landis, who's somewhere here in the audience in the 1980s. There you are. Very important result, because what it means is that multi-layer dielectric mirrors are out. There's no point in spending all of the mass on these extra layers. It's that first layer and the reflectance of it that really counts and gives you the high performance. So it's a very thin sail, not necessarily with a high reflectance. So I wanted to talk about the key trade-off with Starshot, which is really the capital cost of the beam director. And the capital cost of the beam director is figured just for now with the simple equation that it is the product of the area times some areal cost in dollars per square meter, plus the product of the power with some dollars per watt. So that reflects how many dollars per watt a laser costs. And also the storage cost on top of that. So you've got some pulse energy and the dollars per kilowatt hour that storage costs, which right now, with the gigafactory and everything else, is about $130 per kilowatt hour, I believe. This is what drives the top level trade-offs. So this is a beam aperture trade-off where you've got the cost of lasers here and a high cost of optics here, and you're trying to find the right balance between lasers and optics. But traditionally, that's the way the trade-off goes, but also we've got storage involved, so it's kind of this three-axis trade-off. So if you're spending most of your money on lasers, the way to save money is to have a longer pulse time. But if you have a longer pulse time, then you have to store the energy for that, so you've got energy storage. If you are spending most of your money on optics, then you can trade that off against lasers, so you can actually make a smaller beam director that uses more lasers and throws away more energy. But that saves cost overall. So it's a balance between these three things. And the code itself automatically does this optimization. The solution procedure begins with the trajectory integration. That's the core of it. You integrate the trajectory until some minimum acceleration is reached. And as a result of that, you know the time it takes you and the distance that you go, and you know what the speed you're going when you cut off the trajectory is. There's a loop that goes around that, which is a bisection loop, which says, okay, change the diameter of the beam director such that your cutoff velocity is 20% the speed of light. And what you learn from that is your optimal beam director diameter. Then there's another loop that goes around that, which is a golden section search, which varies the beamer diameter between that minimum value, such that you just reach 0.2c. It varies it again to minimize the cost. And then you vary the power as well in order to minimize cost. That tells you the optimal power of the beam director. And then there's another loop on top of that, which varies the diameter of the sailcraft in order to minimize cost. So you end up with these optimal values for many of the system components just by minimizing the overall cost. It's also very computationally intensive to do 5 loops. But the result of the process is beautiful. So this is, it is. So to a certain eye, I guess, yes, if you did it. So for the Centauri system mission, 20% the speed of light, we've assumed 1 micron wavelength, and we've assumed an initial distance that's somewhere a little bit past the orbit of Geo. The sailcraft itself has a 1 gram payload. These are all inputs to the model. So 1 gram payload, there's an areal density which is consistent with about 100 nanometer thickness of silicon dioxide. We've assumed an absorptance which is actually much higher than silicon dioxide has, a 70% reflectance, and a maximum sail temperature. The beamer itself, we've assumed 1 cent per watt. So when you make microwave oven magnetrons, they're actually made for less than a cent a watt. So this is based on the premise that you can get laser costs down to a similar value. We've assumed that optics is also much cheaper in large quantities, so $500 a square meter, and a storage cost of $50 a kilowatt hour, which is a bit past where we are now, but entirely achievable in 10 or 20 years. I've also assumed 30% of the power is kind of scattered or absorbed in the atmosphere. So the results after the optimization is that you have a $9.5 billion capital expenditure, CapEx, that is comprised of $1.6 billion for the lasers. So it's 163 gigawatts of transmitted power. That sounds like a lot, but we have terawatt lasers, and what's really important is actually the pulse energy. So the cost of the energy storage is the long tent pole in this one, which is $4.2 billion, and you're storing 84 gigawatt hours. And the optics is $3.7 billion. But once you've spent that capital cost, the recurring cost of actually firing it is just about $9 million in energy. So why wouldn't you, once you've done the first one, fire it off weekly? You'd have a whole pipeline of sails as opposed to just one. So the optimal sail diameter in this case is 5.2 meters. The sail mass is 5.3 grams, of which one of those grams is going to be the payload, so the instrumentation. Your beam duration is 11 minutes, but your sail is accelerating for 12 minutes, as discussed earlier. The photon pressure is really light, like 36 pascals is a gentle breeze, but the reason you achieve 20% the speed of light is the gentle breeze is going at the speed of light. And your sail is really, really thin, so thin that your acceleration is about 15,000 Gs to begin with. And as you get farther away from the beam director, it goes down to about 1,500 Gs. And that's at 0.2 AUs away, or about 100 light seconds. So to show you what the trajectory looks like, as I said, it's in one dimension. So you start off just a little bit past the orbit, geostationary orbit. You pass the moon within about a minute or so, or you would do if you're actually going in the plane of the solar system, but this is to Alpha Centauri, so you're going down, you're actually in the southern hemisphere, so you're firing out of the plane of the solar system. But if you were in the plane of the solar system, you'd pass the moon and you'd be about halfway to Mars by the time the beam cut off after 12 minutes. Now I apologize, there's a lot of graphs and they're very small, so but this graph here is speed. So the speed initially, you're accelerating, and then as you get farther away from the beam, your speed starts to level off, and it finishes at precisely 0.2 C. Within the first few seconds, you go faster than Voyager 1. You go through the galactic escape velocity. Still inside the first minute, you can escape the Laniakea supercluster. And this is what the acceleration looks like. So your peak acceleration is initially, and then you go down to the final acceleration. The initial acceleration is about what you rate electronics in artillery shells for. So it's something that's done engineering-wise. There's some really fierce sea creatures, obviously. And you're down at about woodpecker head by the time that you've that you've finished. I don't know how woodpeckers remember their own families, with that acceleration. But so there's another dimension to this, and I apologize, it's really small. I can't read it. So that's actually the fraction of beam. So initially, you're close enough to the beam director that you've got 100% transfer efficiency. And then you go down to less than 20% as you get towards the end of the trajectory. This is the kinetic energy of the sail, and it gets just a little bit above 2 kilotons of TNT. That's something that happens with meteors about once a year on Earth. But because this is not a ball, it's just a film, it would probably be a very different sort of event to a meteor exploding in the upper atmosphere. There's another chart, again, this is time on the axis down here. This is the power that is transmitted and received at the sail is logarithmic, so it doesn't change much. And this is the power that's absorbed at the sail. And the power that's absorbed at the sail affects the equilibrium temperature of the sail. So it starts off at its peak temperature, which the optimizer knows, and it goes down from there. Two other aspects of this. So I've already showed you the speed. This is the Doppler shift here. And the Doppler shift, if you were to have a 1 micron source, from the sail you would see a 1.25 micron source in the end, and the reflected photons would be at 1.5 microns. If you were transmitting from the sail itself, you could use an 850 nanometer VCSEL laser, and in the frame of the Earth again, you'd be looking at about 1 micron. This is actually the angular extent of the sail as seen from the beamer, and you go down through milliradians. It's very small. And so what you conclude from this is actually that your sail has to ride the beam, either actively or passively. You're not going to be pointing the beam to hit the sail. You have to somehow entrain the sail to start with, and then the sail rides the beam, because otherwise you just can't make that control loop. It's too far. And that is the full, for people who like details, that's everything. So this is another axis, sail diameter. So we were interested in how the optimizer changes the sail diameter in order to minimize the mission cost. And so you have the sum of all of the parts along the top, and you see there's this minimum here. And the components of that are the storage cost, the lasers, and the optics, and they vary in that way, and your optimum comes out to 5.2 meters. So that's where the 5.2 meters comes from in that point design that I showed a few charts ago. And there's a point here where the behavior of the graph changes, and I just wanted to explain that in case anyone was wondering. There's a couple of different regimes for the sail. One is temperature limited, where the sail is at its maximum temperature, and one is flux limited, where your beam director is using the maximum power that it can. The optimizer allows both regimes to exist, and it actually switches based on what's cost optimal. And that's consistent with fluxes and things like that. I'm not going to get too far into that. So anyway, the system model generates way more data than you can handle, and it's just a case of staring at these and understanding what each quantity is doing to guide the optimization process. One of the other things I looked at is how the mission cost, the capital cost of the beam director varies with the speed, the ultimate speed of your sail. So we were at 0.2 C here, but if you were to derate it, this is how the cost varies. And surprisingly, actually, once you get really fast, the lasers are not the long tent pole, it's actually storage cost, which I wouldn't have guessed, but there it is. Storage and optics. And that's how all of the other quantities vary with the cutoff speed of the sail. Okay, so the Precursor Mission has a different target speed. This one is only 1% the speed of light, so this is something that you would do as you're building up to the full Starshot capability. The payload is now a milligram instead of a gram. The sail areal density is the same. The reflectance is lower. So it's a more modest reflectance. And we're only starting 300 kilometers from the source to begin with. So starting from low Earth orbit, for example. The beamer, we have not assumed such a low laser cost. We've assumed $1 a watt. We've assumed $10,000 a square meter for aperture cost and $100 a kilowatt hour for storage cost, which is essentially what we have right now. So with those assumptions, this is what the cost optimal point design comes out. It's about a $500 million mission, and you're spending roughly half of that on lasers, half on optics. It's a 290 megawatt system, and the array diameter, instead of 3 kilometers, which I forgot to point out before, is 175 meters. So it's something that you would definitely build first, on your way to understanding the full system. And energy storage is only $8 million, it's subdominant. Cost per pulse, $8,000, so you'd fire it often. The sail diameter is 22 centimeters, so it's about this. And it's a 6-minute beam acceleration time. Photon pressure is very low again, but you've still got 10,000 Gs essentially in acceleration. This is all of the quantities that I showed you before, but for this mission and as the trajectory is integrated. So I'm not going to get into that, but data's there. So the vacuum tunnel is what you can do on Earth without going into orbit. So if you have a tunnel which has a vacuum in it, what speed can you get up to reasonably? 70 kilometers a second was mentioned as the maximum speed of, I forget which spacecraft it is. So 70 kilometers was the design speed for this. We've assumed that you're starting a meter away from the laser source. That's probably a bit close. Next time I do it, I'll make it further away. Negligible payload. Aerial density of the sail is the same. And it turns out the solution, so the length of the tunnel that you need, is very sensitive to the absorptance of the sail material. So we had to assume less absorptance from the sail material for this one. But we also assumed 20% reflectance, so very near-term values. The beam director, I assumed $100 a watt, so it's what you can buy lasers for now, essentially. $1 million a square meter for laser aperture, which is not far off from what you spend now. 500. I was very ungenerous with storage cost. $500 a kilowatt hour. You can get it much cheaper than that now. And I also assumed, so there's another axis to the optimization. I also assumed a vacuum tunnel cost of $4,000 a meter. That's kind of equivalent to what LIGO costs or natural gas pipelines. Once you put that through the optimizer, you end up with about a $46 million capital cost, of which is roughly evenly divided between lasers, optics, and tunnel, although the tunnel's the most expensive, and the energy storage costs almost nothing. It's $5, it's 37 kilojoules. But the sail would need to be 1.4 millimeters in diameter, which is consistent with the samples that you can get now, just commercially. Pulse length is 0.15 seconds, and your accelerations are much higher than you would have for the space-based version in order to fit everything within a 5.6 kilometer long tunnel. So LIGO is 4 kilometers, so it's about the size of an arm of LIGO. This is the optimization with sail diameter. So again, the minimum cost is at 1.4 millimeters in diameter. And storage is way down here, it's nothing. So it's about the same as an arm of LIGO. Within a fraction of a second, you're outdoing Voyager 1. You are going faster than the Earth is going around the Sun, and the objective is to beat the heliocentric speed record from Helios B in 1976, that Pete Klupar mentioned earlier. And there's more data than you ever wanted on that. So, in conclusion, there are several solutions to Starshot. We're not picking winners at this stage, we're just labeling everything and trying to organize the schools of thought. For models that are trying to minimize the capital cost, there's a lot of things not to assume, because what I found from doing these simulations is you can't assume a fixed beam cutoff distance, you can't assume a fixed efficiency, you can't assume fixed sail temperature, you can't assume fixed beam duration. So don't assume any of these things for a model if you want to claim that it's going to be a minimum cost system. But the central thesis of Starshot is that the cost of lasers and the cost of optics is going to fall. So this is staged so that dollars per watt falls over time. So you've got $100 a watt assumed for the beam tunnel, $1 a watt assumed for the 1% C mission, and a cent per watt for the 20% the speed of light mission. And similar for the aperture cost, so the optics cost, a falling optics cost, and storage cost is almost there anyway, so I'm not worried about that. So with that, I will open it up to questions.
Questions then, and use the mic.
Thank you.
So when you're looking at dramatically improving technologies, a new technology, whether you're going from ships to aircraft or from semaphores to radio equipment, you're looking for elements of your design that you have assumed are correct and true, but which is not correct or true. But it's operational. But so one of the factor that keeps coming up is that in these beaming technologies is the distinction between near field and far field functioning of the beam. Can you explain how you define the near field versus the far field?
Actually, that's a
Speak to the
question.
mic.
Yeah, no, I'm actually that's a Bob question, but maybe how do you differentiate between the near field
Far
and
field
the
is
far
2d
field?
squared over lambda.
That's an equation.
Okay, 2
So-
times the diameter of the aperture squared divided by the wavelength is the far field. What's the near field?
Oh, okay.
The L field limit? It's short. It's much shorter than near field. And
Yeah.
It's,
Well, that won't.
It's it's operating in the near field because you're operating at the waist of a beam.
So is it empirically defined?
oh yeah, I mean, it's elegantly defined in the 17th century or the 18th century.
Okay, so
Fresnel and others.
there may be
It's the Rayleigh number, right?
maybe a variation in the actual distance in which there's a distinction between near
Oh
field
yeah,
and far
there's a huge difference. The far field is far. The near field is very near. It's just where you're closely coupled to the source is
Yeah.
the physical meaning of the near field. Next question.
Okay, I was interested in your optics cost. Are you tying everything to Atacama Desert optics, where you do have some atmosphere, and what happens if you transfer to a lunar base or low Earth orbit?
So one of the ground rules we were given is it has to be from Earth. And the example that Pete Klupar showed was the Atacama Desert, but there are a number of candidates for where the beam director would be. One of the disadvantages of the Atacama Desert is that to hit Alpha Centauri, you have to go quite low, and that makes the adaptive optics harder. So there's a trade-off for beam director location.
How is science traded off at the top level? Is it traded in the assumption that you have a 1 gram payload, and is that the only trade that you've done for science?
So it's not a science-driven mission. Science is in there, but it was really, can you get there? Like this is, you have to get there first. And so you're able to accommodate, without spending more than $10 billion, you're able to accommodate about 1 gram. It's not started with the science.
Thank you.
What about using 3D technology, 3D manufacturing technology to base the array on Mercury, using regolith as the stock?
The key constraint here is money. If we're
Well-
going to do it elsewhere from Earth, it will not be measured in billions but trillions.
No, okay, but you've got much better power. If you have nano constructors, if you use 3D technology, you're using regolith.
The simple equation was, how much did it cost to do Apollo? $100 billion?
I don't, okay.
It's clearly on
Okay.
the order. We want to do it for 10 times less than that.
All right.
And Apollo just put 16 people on the moon. It didn't even actually build a 5-kilometer array.
This would be a non-manned mission.
Oh, yeah.
Yeah, but
No, but I'm saying the Mercury mission would be non-manned.
The concept you're talking about is unsustainable
it's
economically.
trillions of dollars.
That's why it won't be done.
Okay.
Just as Nixon canceled Apollo for essentially the same reason.
Is there any application for the vacuum tunnel experiment other than as a as a test of systems experiment.
You can use it for Hyperloop.
Are you gonna sit in the, seat?
You get Elon to fund it.
Dr. Parkin, can you clarify something that I seem to have missed with regard to tracking? I believe you said that instead of the beam tracking the sail was going to somehow track the beam.
Correct. It needs to ride the beam. So it needs to seek the axis of the beam, and it can do that passively, ideally, or there can be active systems on board the sail that change some property of the sail to orient it toward the axis of the beam.
And have those tracking technologies been figured into your costs?
No, they have not.
I think you just may have inferentially answered my question, but I need to ask anyway. How you're going to avoid tumbling during boost phase?
Will be considered later today.
And my question is about whether you have or haven't done an environmental impact study. This is the equivalent to about like 10 atom bombs going off, or several the output of several power stations for major industrial cities. So there's got to be, with 30% scattering, you have to take that into account.
Scattering, but not necessarily absorption. And also, there's a lot of sunlight that comes through the atmosphere every day.
Right. Last question?
With your beamer for the Precursor mission, assuming the mission has been accomplished, has any thought been given to using it as an in-system propulsion mechanism and defraying costs of the Breakthrough Initiative through commercialization?
There are
Extensive
many
internal
possibilities,
discussions.
and the subject of many discussions on that front, yes.
Thank you very much.
Thank you.
This session is over.